Okay, let's call this particular circuit circuit 1. And let's talk about the characteristics of circuit 1 first before we look and play with it a little bit. Notice on the left I have a 50 volt power supply that has a 0 ohm internal resistance. Then I come up to a switch. The switch is open. Notice it's even marked with infinite ohms because it is open at the current time. There is an ammeter after that that has registering no current flowing in the circuit, of course, because it is an open circuit. Then at the bottom, I have a 0.1 farad capacitor. And across that capacitor, I have placed a voltmeter to measure how much voltage has been delivered to the capacitor by the circuit. Well, while the circuit is open, you will note that of course, no voltage is across the capacitor. Now, what I'm going to do is close the switch, and in a normal circuit, which would just have a resistor, of course, what you would see is a steady flow of current in that, and there would be voltage drop across the resistor if there was one in the circuit. But here with a capacitor in the circuit, what happens is after the capacitor has attained a full charge, that is essentially blocking the flow of any further charge, and so that will block the current from proceeding in the circuit. So what I'm going to do is close the switch. You probably won't even be able to see a current in the circuit, but you will be able to notice a change in the voltmeter. So here's what I'll do. I close it, and very quickly the ammeter looked like it jumped, and it jumped back to 0, and very quickly the voltmeter jumped, and the voltmeter jumped to a 50 volt drop across the capacitor as it has been charged completely by the voltage applied in the circuit. Now what we're going to do is we're going to move on to circuit 2, where we will change the characteristics of the circuit to the more interesting case of having a resistor and a capacitor. Okay, let's call this circuit 2. And let's look at the characteristics of circuit 2 before we begin looking at this RC circuit. It is a series RC circuit. You'll note that I have a 50 volt power supply with no internal resistance on the left. I have an open switch, which you'll note is marked with infinity ohms because this open switch blocks all current from flowing. Then I have connected an ammeter, and you'll notice it's reading 0 amps because the circuit is open. On the right side, I have a 100 ohm resistor, and then at the bottom, I have a 0.10 farad capacitor. You'll notice that right now I have a voltmeter on that capacitor. Across that capacitor, it has been charged by 0 volts because, of course, again, the circuit is open right now. Now, the first thing you're going to need to be able to do for your lab report is find the time constant of this RC circuit according to the recipe that was discussed for calculating the time constant. And keep in mind that if you multiply the time constant by 4, that sort of gives you an idea of the exponential process by which this RC circuit will operate. So it will be fully charging the capacitor after about 4 of these time constant periods. And after the capacitor is charged, the current can no longer flow. The current will have fallen to 0 amps after 4 of these time constant periods. Now what I'm going to do is you'll notice in the upper left-hand corner, I have a stopwatch. The stopwatch is going to time for us the decay of the current and the growth of the voltage across the capacitor. So what I'm going to do, you'll notice at the bottom of the screen there's a play button. Right now it is on play. I'm going to pause the screen. Oh, no, I'm sorry. I started the screen. I'm so sorry. I kind of messed that up. I have the screen now on the play button is pushed, when you'll notice that the timer starts running when I hit the button at the bottom. So let me pause the screen. Okay, let me reset the timer so everything is at 0. So this thing is ready to play. See, the timer is ready to roll. It's on play. And I'm going to close the switch. And you'll notice there's still no current in the ammeter. There's no voltage across the voltmeter. But if I hit play, then it's as if I'm starting time. So as soon as I hit play, we should see some action in the circuit. So I'm hitting play, and what you'll notice, of course, is that the current is falling. It started at 0.5 amps, as it should. You should be able to calculate what V total, we know what V total is. We know what R is in the resistor. And you'll notice that, let me hit stop, and now we have, at a time of 7.41 seconds, the voltmeter is registering 26.17 volts. So there's now 26.17 volts across the capacitor. Now there's 50 volts total in the circuit according to what you see in the power supply. Where's the rest of that voltage? Well, let me take the voltmeter leads and put them on to the resistor. You will notice that the resistor has across it right now a voltage of 23.83 volts across the resistor. And if you look again across the capacitor, there is a voltage, well, let me put it so that it'll be a positive voltage. I'm going to switch these around a little bit. And I'm getting a 26.77 volts across the capacitor. Now notice again, of course, the current has fallen to 0.24 amps at a time of 7.41 seconds. Now remember, again, if we were to use the formulas and calculate these parameters, you should see a nice agreement with what the theoretical prediction is compared to the measured predictions. Now what I'm going to do is I'm going to hit play again to change the time, and we should notice that the current continues to fall and the voltage across the capacitor continues to grow. So I hit play, and I notice these numbers are growing for the voltage across the capacitor. I notice the numbers are falling for the current flowing through the circuit. And you should also notice something else. It's starting to slow. The voltage gain in the capacitor is slowing. The current fall in the ammeter is slowing, even though time is progressing at the normal rate that it has the whole circuit. I'm going to hit pause again, and you should take down these characteristics at 18.96 seconds. Now the current has fallen to 0.08 amps, and the voltage across the capacitor has risen to 42.49 volts. Now remember, again, we are delivering a total of 50 volts in the circuit. Where's the remainder of the voltage being dropped? Well, if I look across the resistor, I find a VR of 7.51 volts. Now, again, we can hit play and let it progress again. Notice I'm measuring the voltage across the resistor. Notice the voltage is going down across the resistor. Notice the current is continuing to fall as I let this progress. Now there's less significance in the ammeter than the voltmeter, so the ammeter should get to 0 before the voltmeter does. But let it fall all the way to here. Let's take one last reading. At a time of 29.31 seconds, I'm getting an ammeter reading of the current of 0.03 amps. Not very much significance to that reading. I'm getting a V across the resistor of 2.67 volts, and I'm getting a V across the capacitor of, I think you can predict what that should be the remainder of the voltage in the circuit. That is 47.33 volts. Okay, now what we're going to do is we're going to stop and pause our video, and then we're going to move on to the next circuit and see its characteristics. All right, let's call this circuit 3. Let's first review the characteristics of circuit 3 before we play with it a little bit. Again, I have a 50-volt source of power on the left. I have an open switch. I have an ammeter registering no current right now. On the right, I have a 100 ohm resistor, as before in circuit 2. And at the bottom, I have 2 capacitors, each being 0.1 farad, but you should notice that these capacitors are hooked in parallel. When you're hooked in parallel, you have the same voltage across you when you're hooked. And you can see right now, I have the ammeter hooked, or I have the voltmeter hooked to them, and I'm getting 0 volts across either of these capacitors because the circuit is opened. Now, 2 things you're going to need to do first is you need to find the equivalent capacitance of this parallel capacitor circuit using the rules for parallel capacitor equivalent capacitance. So first find the equivalent capacitance of this. Then you need to find the time constant for the circuit. And of course, remember that is tau is equal to R times C, but in this case, it'll be equal to tau equals R times C equivalent. So you need to find the time constant for this parallel capacitor in series with a single resistor, and you should be able to do that. Now we'll notice I have the stopwatch started. It's not running yet because I have not hit play on the circuit. When I hit play on the circuit, before I do that, I need to close the circuit, because if I hit play on the circuit now, as a matter of fact, let's just do that. I hit play, and notice the stopwatch has started, but there's no current flowing because the circuit is open. I'm going to stop the play, and I'm going to reset the stopwatch, and now I'm going to close the switch, but you'll notice nothing is again happening because I haven't hit play on my circuit. Now when I come down here and hit play, we should see the current immediately start out at 0.5 amps because it's a current being produced by the resistance divided into the voltage, but that current should immediately begin to fall because of the RC characteristics. And we should notice that the voltage across the capacitors grows as time progresses. Now I think another thing I might want to do is put the capacitor or the voltage across the capacitors like that to get a positive voltmeter reading, and we should note that that voltmeter reading should grow. I'm going to now hit play, and let's watch that occur. Now another thing you should notice is that the current is falling from 0.5 amps as we have an exponential decay of the current. I have a growth in the voltage across the capacitor, but this circuit has a different time constant than did circuit 2. I'm going to hit stop at this particular point, and you should register these values for your lab report at a time of 7.62 for seconds for the clock operating. The current has reached 0.34 amps, and the voltage across the parallel capacitors, meaning each of them has this voltage across it, is 15.84 volts. Now, here's an interesting thing. Let me take the red lead to the other side of the capacitor, and you'll notice the total voltage is being dropped from the top of the resistor to the backside of the capacitors in parallel. If I go to the resistor only, you will notice that VR is equal to the remainder of the voltage that the capacitors have not yet received, and that will be the 34.16 volts. Now again, I'm going to go back across the capacitor in case you missed it. The capacitor has charged up with 15.84 volts. I'm going to hit play again. Time resumes to progress. Current continues to fall. Notice that the speed of the current falling and the climb of the voltage is different than, again, circuit 2 because of the difference of the RC time constant for this parallel capacitor circuit. I'm letting it run a little while longer. We're going to take a second data point. I'm going to hit stop. So for your report, you should note that at 17.22 seconds, I have a current of 0.21 amps. I have a voltage across the capacitors of 28.66 volts. That's how much they have received to charge with. And I have the remainder of the voltage being across the resistor. So let's quickly check that. It is 21.14 volts. Now I'm going to start it again, and we should notice I'm just going to leave the voltmeter on the resistor. The voltage across it should fall as the current falls, and of course that's because there's more voltage going into the capacitors. I hit play, time is progressing. You'll notice the current is falling across the whole circuit, as well as the voltage falling across the resistor as more and more of the voltage is being consumed by the capacitor in this RC circuit. Remember, as I said before, the significance of the ammeter being less than the significance of the voltmeter. That means that the current should reach a value of about 0 way before the voltage reaches a value of about 0. Notice another thing very important, the exponential decrease of the fall of the current, the exponential decrease of the fall of the voltage. The numbers simply are not moving nearly as quickly as they were early in the time constant of this circuit because of the fact that that's just the characteristics of how these behave. I'm going to take one more data point for our lab reports. Let's wait till the current reaches 0.05 amps. Oh, I didn't, I cheated. Okay, let's just take this point. When I have 0.06 amps for my current, I have a voltage across the resistor of 5.71 volts. I have a voltage across both capacitors. Each have a voltage across them of 44.29 volts across the capacitor. Now what I'm going to do is I'm going to move on to circuit 4. Okay, let's call this circuit 4. Let's first again review the characteristics. It's again a 50 volt power supply. There's a switch, which I happen to have closed this time, but I am not playing the circuit. It's not, I haven't hit play on my screen yet, so there's no voltage or current reading, and that's really cheating because time hasn't evolved yet. We're at time 0 right now. I have an ammeter that's registering 0 amps. I have again a 100 ohm resistor on the right, and I have 2 0.1 farad capacitors. This time the capacitors are hooked in series. When the capacitors are hooked in series, you should be able to determine a CEQ for them using the recipe that we discuss on the slides. So you're going to need CEQ for these for your lab report. Then you will also need to calculate tau EQ, if you like, the equivalent time constant for this circuit, which would be R times CEQ. You will note, again, this is a different value than we used in either circuit 2 or circuit 3. So this should have, the circuit when we operate it, should have different characteristics of behavior in terms of how time evolves with the charging and fall of current based on the difference in the time constant of this particular circuit. Okay, I'm ready to operate the circuit. When I hit play with the switch closed, you should see immediately the current jump to the beginning current, in this case of V over R of 0.5 amps, but then it should quickly begin to decay away as the two capacitors charge, and we can note the characteristics with time that you should be able to calculate using the equations discussed in the slides. So here we go. Time is progressing, current is falling, voltage is gaining. Now you'll notice I'm measuring the voltage across both of the capacitors. Let's stop it here and take our first data point at a time of 4.4 seconds. You will notice that V across the two capacitors is 29.55 volts. Of course, if I were to measure V across one capacitor, it would be a value of 14.77 volts, or half the voltage drop across the two capacitors. Now if I go up here and measure the voltage drop across the resistor, I get VR equal to 20.45. Now, of course, if I compare that number to the voltage, let's go all the way across. Why don't we do that? Let's start again here, and let's go all the way across all the components. You'll notice that's a total of 50 volts dropped across all three, and across the two capacitors, again, it's 29.55. So everything sums just the way it should be summing in this circuit. Let's continue to progress time. Notice one thing you should verify is that with the different time constant in this circuit, the time it's taking to charge the capacitors completely is not nearly the same as the time it was in the previous circuit. Now, when the two voltages across both capacitors has reached 43.3, or almost all of the voltage possible, the current has fallen to a value of 0.07 amps, and the voltage across the resistor, of course, must be the remaining. That sounds like 6.7, but let's verify that. And you see, yes, it is 6.7 volts being dropped across the resistor because of the very low current being fed through that resistor. Now, let's progress time here and let's see if we can get the current. Notice it's going to be falling slower and slower and slower. These last little bits of the current I'm attempting to remove are going to take a long time because we're on the very lengthy part of the exponential curve. Notice the voltage has fallen across the resistor down to around 1 volt. Notice how dramatically the voltage is slowing. The ammeter is still registering a little bit. The voltmeter is heading down towards 0. We don't have anything better to do. Let's just continue to let that fall. Notice again how much slower. Finally, the voltmeter, the ammeter has gone to 0, but that's due to significance of only of that ammeter. The voltmeter is still registering voltage, and notice how slowly it is decaying. We're going to get I'm just going to milk every last bit of voltage, saying the current in the resistor has dropped at least to 2 digits of accuracy to 0. We're getting really close. I know you don't have anything, or you don't want to sit here and wait all this time out, but let's get the last drop out of the voltmeter. Time is still progressing. I still got a little bit of voltage register, and now it is registered at 0. But let me see if I take the voltage across the two capacitors, we should get that all the voltage, and there you have it. There's 50 volts across the two capacitors. by the time we reached, notice the time of 47.73, we have a voltage across the two capacitors of 50. We had a voltage across the resistor of 0. And if I measured the voltage across only one capacitor, you would, of course, get 25 ohms across a single capacitor. Okay, now what we're going to do is we're going to stop this and move on to our last circuit. All right, let's call this circuit 5. And in circuit 5, you'll note I have again my 50 volt power supply. It leads into an ammeter, which right now is registering nothing because I have stopped the elapsing of time. You'll notice, as a matter of fact, I didn't start it up here. Let me start the time, and you'll notice the stopwatch is not rolling because I have to hit play at the bottom. I have the circuit closed. I have the switch down, so the circuit is complete. But now I have the resistor and capacitor hooked in parallel. Now the RC characteristics only work for the series connection of the resistor and capacitor. So this is a little bit different of a setup. Again, I have a 100 ohm resistor. I have a 0.1 farad capacitor. The voltage across the capacitor right now is registering 0. And you'll notice also there's a current, there's an ammeter in this part of the junction. It is registering 0 amps as well. What I'm going to do is I'm going to start time evolving, and we'll see what occurs, what transpires for the readings of the voltmeter and the 2 ammeters. So I hit play, and what I notice is that instantly the ammeter connected on the left-hand loop is at 0.5 amps. The ammeter in the right-hand loop is at 0 amps. You will also notice that the voltmeter is registering a 50 volt drop across the capacitor. Now if I move the voltmeter leads across the resistor, unlike it was when they were hooked in series, you'll notice there's a 50 volt potential drop across the resistor and the capacitor. When you hook components in parallel, they get the same voltage across them. So I have charged the capacitor with 50 volts of potential. Notice no current. I'm looking down here. This ammeter is reading 0 because the charged capacitor is impeding the flow. My voltmeter isn't quite registering correctly. Didn't put my leads on. Now it is. I'm registering 50 volts across the capacitor. I'm registering 50 volts I had before across the resistor. The current is still flowing in the left loop because the junction is essentially got an infinite resistance on the right loop due to the completely charged capacitor. Now what I'm going to do is I'm going to stop the evolution of time. I'm going to reset the time that things are occurring. I'm going to open the switch. Now the left loop is open, but the right loop should be a connected loop of circuit. The power supply, which will be in that right loop, is due to the charge on the capacitor. So what I'm going to do is I'm going to let time evolve, and what you note is now both the current and voltage are dropping due to the RC constant. I stopped them, and let's talk a little bit about what's going on there. I have an RC constant in the series circuit of the 100 ohm resistor with the 0.1 farad capacitor. Initially at time 0, the capacitor had 50 volts of charge. And if you noticed initially when I pushed the button, there was a 0.5 amp current flowing out of that capacitor. But now after an evolution of 3.18 seconds, the voltage in the capacitor has fallen to 36.38 volts. The current flowing in the circuit is fallen from 0.5 down to 0.36 amps. And if I were to measure the voltage drop across the resistor, again, it is 0.3638 volts as well. Okay, so I'm going to go back across my capacitor again, and well, let me put it in a positive sense by putting my leads like such. Now let's begin the evolution of time. Again, you should be able to calculate how fast the voltage and current are falling from the mathematical expressions that we have for the change in current and voltage. I'm going to stop time after an evolution of about 10 seconds. We'll make that 10.29 seconds. At that time, you should note that the voltage, the capacitor is continuing to discharge. It has 17.87 volts left across the capacitor. The current has fallen to 0.18 amps. And if I were to measure to that significance, if I measure across, notice if you take this number times 100, it's a little bit more than 0.1787. Again, that's because of the significance of the ammeter. If that ammeter had more digits, I bet they would say 0.1787 amps, so that the voltage drop across the resistor is the same as the voltage that the capacitor is delivering, and you can see that it is there, of 17.87 volts across the resistor. Let's again let time evolve. Time is going forward, but the current and voltage are falling as the capacitor drains in this circuit. Let's let it run just for a few more seconds here. Then we'll take another time stamp of the characteristics. Again, remember, you should be able to compare these experimental measured values to the theoretically predicted values, and they should do very well. So at our last time reading at 19.71 seconds, the current has fallen to 0.07 amps, and the voltage across the capacitor, the remaining voltage in the capacitor, is 6.97 volts. And if I would let time evolve more, it would drain down to 0 volts of current held in the capacitor, and there would be no more 0 volts of, not current, 0 volts of voltage contained in the capacitor, and there would be no remaining current flowing in the circuit.